Hello, good evening. I was on holiday during 15 days and I miss your broadcast the most. Why, thank you. But you have to stay until the end, you know? Or watch them on. I put all the videos on YouTube. I think you can watch them all, I'm not sure. You know, there are copyright issues because of the music, whatever. But you can read the source code and you can play with it. That's probably the most important thing you can do. And I can't check that, right? So you might as well say that you did. Tonight I'm going to work on thread destruction and then mutexes and condition variables. And maybe I will even have time to integrate the code of a shell I wrote somewhere else, so that I will actually have commands in the kernel, which means that the kernel will be almost complete. The last piece that would be nice to have would be timers, but I'd like Metal Snake to work on those instead of me, because I've worked on all the threading stuff, and he's busy, so yeah. So I'll keep the timer stuff for him. And so normally this should be like one of the very last streams about X1, and so very soon I'll probably go back to X15. Like maybe I'll take a break the rest of December because I need a break. But very likely in January I'll be working again, and I'll probably have made progress on X15 by the time. So let's get started. Oh, I changed the layout of the sources so that they're more organized. Basically, this looks like this now. You have sources, library code, include files. Here you can find the standard files that we add to the kernel so that we implement some of the standard services normally provided by the implementation. What I call the implementation is everything that implements C from the compiler to the C library, for example, because we don't have them here. Well, we have the compiler, and the compiler provides us with some headers that are required in freestanding environment, but the freestanding environment is very limited. So everything that is added, but which is also standard, I've decided to put it there. So yeah, assertions, printf, basically, memcopy, you know, that kind of stuff, but only the declarations. This is code that was pulled from my other library. I say other, but there is only one, actually. This library here, basic multithreading library for C. So you can find a couple of files here, and the way this library is meant to be used is that you pick what you need. So I picked the format files, the macros, and the linked list. And I don't even need list sorting, so I didn't even pick the C file. Just the header. The header is enough. The shell will also be picked from this library and put there. And this is the code of the kernel. So now it should be easier for people to know what's what, and to, I don't know, yeah, that's really the point. Okay, so last time I worked on sleep, wake up, yield if needed, and now I want to work on exit and join. So here is how a thread lives, basically. You create it. As soon as creation has succeeded, the function is run with those arguments. When the function returns, or when it explicitly calls thread exit, the thread dies. Not immediately, but it never returns from exit. And now that I'm saying that, I should actually immediately think about declaring it with a no return attribute. This thing here. Oh, I had it in the header already. No return. This tells the compiler that when this function is called, the compiler can assume that it never returns and optimize the generated code accordingly. What else do we have? Okay. So yeah. If you look at the POSIX API, create, pthread create, the new thread terminates in one of the following ways. It calls pthread exit, specifying an exit status. We won't implement that. We let that to the user. If the user wants an exit status, he can just, fill in some structure member and return. So returning from the start routine, this is equivalent to calling pthread exit with the value supplied in the return statement. Again, we don't have a return value. Okay, we just have void here. In the type here, we only have void. We don't have void pointer. It is cancelled. We have no concept of cancellation. Any of the threads in the process calls exit. Again, we don't have the concept of a process. So basically, these are the only two ways a thread can terminate. Calling thread exit explicitly or returning from the start routine. So this is actually very easy to implement from the terminating thread side, like this. Done, right? And that's really how library is implemented. They basically put this call right after calling the function. Okay, and so now the compiler also knows that this function never returns, because this one never does. And we have this function here which is thread join, and thread join is basically synchronization on termination. So when a thread terminates, you don't know when it terminates. You can't rely on I don't know. For example, if you had a variable terminated in shared memory, you can't rely on the thread actually being terminated when this variable becomes true, because this variable would be set to true here at the end of the function, and then the function would return, but that takes time, and during this time the thread is still running, maybe running alive. So join is the counterpart of exit. You basically wait that the thread is actually terminated, and then you release any resource that the thread had. And it acts as both free and wait, or rather wait and free, but atomically. Now, I'm wondering if we should implement detached threads. Detached threads are threads that you cannot join, and that's why they're called this way. So when a detached thread calls exit or returns from the function of the thread, it is automatically joined by something else. Well, actually that's the implementation. The semantics is that you don't join detached threads. The threads will be taken care of at some point in time that cannot be synchronized on. So basically you create detached threads when you really don't need to synchronize anything against them. And normally you shouldn't. Like, detached threads are normally something that you use for convenience. In Unix, for example, in terms of processes and the organization of the system, you have the wait call, the wait system call, which is basically join. It's basically wait and destroy a terminated thread, except that it was extended so that you could wait for other events, not only termination. But when it is for termination, it's very like it's the process counterpart of join. And thread exit obviously would be the exit system call. So when you call exit as a process, if another process calls wait, it will return and get the status, and all resources will be released. Also, when you see a zombie thread, so that's an interesting thing, a zombie thread or a zombie process, it means that the process has returned, so exited, terminated, whatever you want to call it, but wait hasn't yet run. So the thread of the process is pending destruction. It's a zombie. I don't know if I will have a zombie state or a dead state. The reason is that on this system we have a single processor, which means that we may very well be able to implement destruction in a single pass. And maybe we won't even need to release anything in the join code. I don't know yet. And I wanted to talk about something else, but I don't remember. Maybe I did already, I don't know. We'll see. If I don't remember it, I guess it wasn't that important. Hello guys, Spaghetti and Root. Alright, so how am I going to implement this? Thread create is here. Oh yes. No return. What else needs no return? Well, it would be the user functions, so no. Here it's not needed, only on the declaration. Okay. So the first thing we probably need is the current thread, because thread exit implicitly applies on itself. Talking about zombie process, yes, zombie processes. And that's the reason why you have them, because you can't avoid that transient state. In order to avoid that transient state, you would need to lock up your whole system to make sure that destruction would occur first. And that's not very efficient. Okay. So we need some synchronization, because a thread can't destroy itself. So we need a list of threads to destroy, I suppose. Either we can make the idle thread take care of this, but I don't like this idea, because if you spawn a lot of threads and destroy them thinking that they will be recycled, if you still use 100% of the processor, the idle thread is not going to run, and so your terminated threads are not going to be released. So I'm going to create a special thread that I'm going to call the Reaper, which will do this. The same way we have idle here, we have the Reaper there. Okay, so let's imagine that we do have the Reaper. We also need the run queue, obviously. Okay, so basically thread exit is going to be like thread sleep, except that there will be another state. And yeah, basically that's it. As the on-prod server, there are a lot of zombie thread, like we can put napalm in it. Major zombie processes. A lot of them? That's not a good thing. It's a mistake. Oh yes, that's reminds me what I wanted to show you. So this Reaper thread I was talking about will be used for detached threads. So apparently I want to create them. Do I? No, I don't. I don't want to create them. So let's kill the Reaper. Let's force the destruction of threads by the user. Okay. If you don't wait on the process on Unix, what happens is that the init process with PID 1 becomes the parent of the process that is like not waited upon. How could I say that? Imagine that you have a hierarchy of process like I have here, and so you have init, then you have a process, and then you have another process below it. So the second one is the parent of the third. If the parent dies, the third becomes the child of init, and not the child of the grandparent, but directly the child of init. And the only job of init, well, it's not the only, but one of the jobs of init at this point is to wait on children. So basically to call the wait system call on children processes. And that would have been my Reaper thread here. So I could do it, but instead I'm going to simplify things by restricting the interface. So I'm going to state in the specification here that when you have a thread, you have to call join on it. It's mandatory. right? No detached threads, and that's it. I'm going to get by with this. Which would be the same as on Unix saying that you need to wait on processes in order to clean their state, otherwise they're going to remain zombies forever, like is happening on the server of Blood, for example. The server had 200 megabytes of RAM free and the swap was full. Oh, it's not possible to call reboot. Yeah, that's a really bad situation. A really bad situation. Well, 200 megabytes of free RAM is good, actually. Usually it's much less than that. When you have, like, when your swap is actually full. Because your swap might be full for other reasons. You also have to look at the cache. Remember this thing? That yellow thing here? And actually the blue one too, but the blue one is usually small compared to the yellow one because we mostly cache files and not directly disk blocks. But that's really what you want to look at. You can't say that your RAM is full if it only contains cache, because cache can just be flushed. Oh, 4 gigabytes on buffers. Oh wow. That's a problem. Unless you actually have something that uses a disk directly, which would be surprising, but sometimes there are a few applications that do that. Impossible to kill -3, that would be -9, and don't rely on numbers. Sick quit, yeah, no. You want this one, sick kill. Sick kill tells the kernel to actually kill processes. It's not a signal that can be catched. Sick kill is basically, yeah, we do have, well, it's implemented with a signal, so I'm not going to show it, but sick kill is just a way to tell the kernel directly kill that thread, don't even send it the signal. Sick kill didn't work too, yeah. So that's because zombies must be cleaned with a wait system call. And the only process that can actually call wait on other processes is the parent. You have to be the parent to wait on your children. So yes, in this case you have you probably have a bug that uses global resources, and that's really, it's the same thing like when you have memory leaks in a process, except that it's another kind of resource and it's global to the kernel. Do you have 32 gigabytes of RAM? Yes, I do. And on my server I have 64 of ECC memory. And that's the main reason why I have so much. It's because I want ECC memory. ECC meaning error checking and correction, I think. And the reason I want ECC memory is because when you write very sensitive code, like an operating system kernel, for example, you really don't want bugs to occur because of a bit flip. And I've seen that more than once. And when you have been beaten by it, you don't want it to happen again. So I'm using ECC memory on all my main machines. Like the only one I don't have ECC memory on is my laptop, and I do develop on my laptop, but I don't really test on it. All the tests are on this machine or my server in virtual machines. Okay, so decided I will not have a Reaper thread. So this means that I need to implement thread exit and thread join in parallel, because they're going to work together. They're just both sides of the same operation, actually. So the thread that calls exit must sleep. That's the first thing it has to do. So let's take a look at how we implement thread sleep. Okay, it's basically like this. Indeed, preemption must not be enabled. Yeah, it's actually different from sleep. Here with sleep, we want preemption to be disabled and to be exactly 1, because we accept thread sleep to be used to synchronize with another thread, and so to share data with that other thread. Which means that in order to protect that data, we want to disable preemption. And so when entering sleep, the preemption level should be exactly 1. And when we go out of sleep, we can recheck that value again, knowing that the preemption level is 1. And it makes checking atomic. The value cannot have changed between the time of wake up and waking up from the sleep. Here it's slightly different, because there is nothing to, like, the thread calling thread exit has nothing to synchronize against the thread calling join. This will all be internal in the implementation, but not outside the functions themselves, not in the user code. So the user should not be aware of that, which means that here we only want to make sure that preemption is enabled. Thread is running. We could do that. It's kind of useless though. Especially here. Yeah, we have set sleeping, okay. So we probably want to move that assertion here once we have disabled interrupts too, just before we change the state. Okay, same here, I suppose. So we do want to disable preemption and interrupts, both of them, because we want to create a strongly protected critical section against both other threads accessing the memory of this one and interrupt handlers too, because interrupt handlers might call thread wake up, and is that a good reason actually? Is that a good reason? So that's something, yeah, I haven't talked about it much. But the run queue here, when accessing the run queue, it must be with interrupts disabled, and the reason why is because we could call thread wake up from an interrupt handler. And this is really important, because if you can't do that, it means that you cannot wake up a thread when you have an interrupt, which is essential. So thread wake up has to run from an interrupt handler, which means that the run queue here must be accessed with interrupts disabled. When you do it from a thread, so that the thread strongly synchronizes against interrupts. Okay. And so because we are going to sleep, we need to disable interrupts too. Did you implement data structures yourself? You mean the linked list and... Yes, I did. You can find them here, in that small library I wrote. So yeah, I think they're mentioned in the below the stream. I'm not sure actually, but basically it's sin.net. This is my website, and you have my projects, and I should add X1 someday. And it's basic modules library for C, and you have all these small modules in it. And so the list implementations are very close to Linux, except that I also have an S list here that Linux doesn't. But the plist is like an older version of the one in Linux, because now it uses a red-black tree, if I remember correctly. The W-link list is very, very close. So is the hash list, which I could call an half list too, which is usually used for hash tables. Hash functions, printf, scanf, errors, circular buffers, bitmaps, arbitrary length bitmaps. Yeah, both AVL and red-black trees and radix trees, and that's all I think. Yeah, macros. Macros are cool too. So this is a very handy library when you write embedded stuff, because the code is really meant to be used in small firmwares. So there is very little memory allocation, and it's really reliable. It has been thoroughly tested and used in multiple firmwares already, and so yeah, and the license is completely permissive. So if you want to reuse that, like if you're an engineer working on embedded stuff and you lack that kind of data structures, help yourself. I don't think you'll need trees, because usually you don't have much memory in embedded devices. So you don't need to handle lots of objects, but they might be useful someday. Alright, so we want the flags again. We're going to disable interrupts and save the state. Can this function be called with interrupts disabled? Yes, I don't see why not. Okay. Also, do we actually want to save the effects? I don't see the point, because we're not going to wake up, which means we're never going to restore interrupts. So we make sure the thread is running. Thread set dead, and here we introduce our new state. Okay, now we're going to call thread run queue schedule. So basically we do the actual scheduling on the run queue. And normally we should never wake from there. So obviously this is not all, because we also have to signal that the thread is dead. There are two cases. Join could be called before or after. If it's called after, it's okay, it will see that the thread is dead. But if it's called before, it has to wait, and so we need to wake it up. So we need to increment the thread structure to provide that information. We do have panic, don't we? No, yeah, we don't. We do. Okay. Alright, so let's add this new thread state. Okay, we probably will need to check that it's dead, but we'll do that later. Okay, so let's write, actually, do I really need to implement thread join at the same time? I don't think I do. We'll see that after, in multiple passes. Let's try and see what happens if thread join is called after. Well, actually, after would be the implementation itself. So let's see what happens when it's called before. It's gonna sleep, okay, and it's gonna wait. It's gonna wait on something. We need to provide that variable, and that variable would be the state, actually. Okay, so what we need to do is provide a pointer to the waiter, the joiner. Okay, this node here is used in the list for scheduling, so it's quite heavily used. The preemption level also, but these ones not much. These ones are called. Okay. So here, now that we have set the state to dead, we could just wake up the joiner. Thread wake up thread joiner. The joiner, well, there might be no joiner, which means it might be null. So let's check thread wake up and add a check here. If thread, what if not thread? Or thread is self, something like this. Okay. Did I forget to close something? Apparently I did. No? Oh, okay. So if the thread we want to wake up is null or is the thread itself, the current thread, we do nothing. Obviously there is either no thread to wake up or the thread is already running because it's trying to wake up itself. Why no dynamic array in the library? It's almost always better than the list, memory-wise, complexity-wise. I strongly disagree. Very strongly disagree, especially in the kernel, because of memory fragmentation. especially in a kernel like Linux, or the one I wrote, not this one, but the other, X15, which uses a slab allocator, which is an allocator that is specifically meant to allocate objects. It's an object caching allocator. So you don't have, for example, you can't realloc. You can't resize your blocks, which means that every time you want to realloc, you have to move stuff somewhere else. So it's quite simple. There are almost no... I could say that I'm almost sure that there are no dynamic arrays in Linux, except, very weird cases, because there are weird cases, like the per CPU array is a resizable array in itself, but it's probably not what we would call a dynamic array here, so no. Also, dynamic arrays are really easy to implement, in my opinion. Also, if you want to use them efficiently, unfortunately, very often you'll want to you'll want to pass pointers in them. The FreeRTOS queue is a good example of that. Let's take a look at it. Okay, this is the API basically, and they have a description. Although this is the reference. That's not exactly what I'm looking at. Looking for. Yeah, I didn't want to find the reference. Q seems broken. They're not. Ah, that's annoying. They had a very good description. Maybe that's it. Yeah. Okay. So in FreeRTOS, for example, a queue is basically a dynamic array, and that's how you pass elements in it. And so internally, it's a ring buffer. The problem is that when you want to actually pass data, you copy the data into the queue, which is actually a good thing, because in embedded systems, especially from interrupt handlers, you can't allocate memory from an interrupt handler usually. I mean, you can, but you shouldn't, because most allocators are not real-time, so if you are in a real-time system, or even if you're not, but you're careful about your interrupt handlers because you don't want too much latency. Too much latency may make your system unusable. It may mean that other drivers miss interrupts. So you really want your interrupt handlers to be short. So you want to avoid memory allocation in them. Also, many times you just can't allocate memory because the memory allocator has to sleep, and you cannot sleep inside an interrupt handler. So the API here copies the data into the queue, and then copies the data from the queue to the second task. So it's not very efficient memory-wise because you have those copies. For one reason. Here it's a good thing because there is this case. It's meant for this case where you copy from the interrupt handler to a task. By SNN, you'll have to tell me what this means and how to pronounce it. But thanks for watching and stopping by. Okay, so that's one thing. The second thing is how do you handle holes? How do you handle removal? Do you resize all the time? Do you have a threshold below which you're going to resize, or not? Are you going to just let lots of slots empty, unused? No, it's not a good thing. Can you give me your reasons, Redov, for saying that a dynamic array is better than a list? Because you say that it's memory-wise, complexity-wise. So complexity-wise, again, I disagree. It's good when you it's good when you have an index, for example, obviously, because in a list it would be ON, and in an array it's O1. So in some cases, it's the right data structure to have. I agree. It's like the fastest for lookups. But as soon as your container grows, it becomes very difficult to maintain. Realloc is not a simple thing to implement in many systems. I mean, complexity-wise, I'm not talking about the implementation. I'm just saying that you just need to allocate copy and free, and that's expensive. That's actually O and 2, and not even big O. Whereas lists, as long as you don't have to look up, it's a 1 all the time. Short version for my name, Sinan. Not experienced in kernel, and I can see why with the step allocator why a list is correct, especially if you must do. Well, not always a list, but not an array. If you must allocate objects, but with a classic heap, I assume allocator lists are terrible. Again, I disagree. It really depends on how you use your objects, because even if you have an implementation of realloc that is efficient, which means that it can resize instead of allocate, copy, and free. First, this is not a guarantee, which means that the worst case is still an allocation and a copy. The free is like, we don't care too much about the free, it's usually fast. Because the cost of the new OS, OK with k greater or equal than n with n size of the array, k number of node. But for what operation? You're giving a complexity, but you're not saying what operation it applies to. Most operations in the list are O1. The only one that is not is a lookup. So you can use something else for the lookup, like a tree. Let's assume the worst case for the array, you allocate copy and free, yeah. So that would be just for resizing, just for adding new elements. With a list, it's always O1, no matter what the size. So that's already a very good case, a strong case for the list. Yeah, I understand what you mean. But if you want to talk about that, I don't know, if you have a Discord or something, maybe I could join. Although I have problems with my Discord on Linux. Not sure why. A single add in the list is not exactly O2, well, O1, because the allocation of the node has a cost. Yeah, I agree. So it's still O1 because we consider the allocator, the allocation itself to be a single step. But I agree that internally it depends on the allocator. But it's the same problem for the array. I mean, to allocate a single, even a single resize, without a copy, it would be the same cost. So that cost can be, we cancel it out, we don't consider it. N nodes with a heap alloc is O(n) log n, assuming allocation is log n. I can't even assume allocation is log n because many allocators are almost always O1. For example, the slab allocator just grabs the first slab that matches that is partial and that matches the object. So it doesn't even have to look up. The only times where it's not O1, it is when it has to make more memory from the backend. And you can't assume that this operation is logarithmic. But the worst case is, I agree, most of the time the backend is virtual memory, and virtual memory is usually managed with a tree. So let's say that it's logarithmic, okay. But again, I assume, I don't count this operation in because you have that in both cases. So I just cancel them out and ignore. And so the ones that are not the same is for the array, the entire copy of the array. That would be one. So what you would do, for example, is that you would use realloc with an exponential size. And so that exponential size would be, it would make allocation logarithmic, I agree. where growing an array would be on plus log n. Well, so here you're mostly basing your assumption on the allocator, assuming the same allocator and n copies. I really don't see why. N plus log n. I see the n times log n, but I don't see the n plus log n. Hello T-Blood. I just love how you enter here and talk about your own problems without even saying hello. An apparently valid pointer giving a seg fault. ARM64. So why n plus log n? Sorry guys, I'm just in the talk right now, not coding, but I'd like to finish that. N plus log n. Hello Foss. Could I talk on Discord TS3 or something? Quite extensive writing. Yeah, I understand. Well, if you have one, I don't. I have a TS3. Yeah, I could. Yeah, okay. Let me give you that. Hello. Hey. So, just the problem though, I'm not sure people are gonna hear you because I have some music here, so I'm gonna shut it down.
So I was mostly talking because, okay, well, I'm not a computer science student or anything, but I follow some course for fun at the university.
Okay.
And I mean, you often heard teacher say thing and mostly on array, right? They have this thing where they will say, okay, for inserting a element in a list, for instance, it's O1, and for inserting an element in an array, a dynamic array, is ON. And that I agree if you only consider the worst cases. But what I wanted to say about that is the big difference between an array and a list, like what is interesting about the dynamic array is the fact that you only make allocation every n insertion, right? So the idea is that let's say you have n element in
I'm not
the
sure I
array.
follow. Every n insertion? Why?
Yeah, but I mean, you make the reallocation of the array every n time, right? You don't make an allocation every time. So
So
let's say,
you resize exponentially, right?
yeah, exactly. I assume a
So
2n
it's not every
for
n time. It's just that you use a
yeah,
base.
yeah. Let's say you have n element. The next time you will resize is after n insertion. That's what I meant. So yeah, let's say
So that would be
we have
base 2, basically.
Yeah, exactly. Let's say
Okay.
we have a dynamic array base too. So let's assume you just reallocate, right? So you have n element in your array, and the capacity of your array is 2n. So that means for the next n insertion, or whatever, it will take O1, right? Or just the copy of the object of the
Okay.
pointer or whatever. And then when you will make the next add, it will take, so you will have to allocate the new buffer. And let's say realloc don't even exist. Like you don't even have this smart thing where like if you can grow, you grow. But let's say you just reallocate another object somewhere else, and then you copy your 2n element. So that means for inserting n element, so the first n were completely free because it was just the copy of the pointer of the object. Like if you have an array of pointer is like extremely fast. I mean, you mostly just move a register into a memory space. So that means the cost of adding n element where your array was of size n at first was mostly an allocation plus a copy of this to n element, right?
Okay.
So and I assume there that the allocation. That's why maybe my assumption is a little bit false, is because I assume the cost of the allocation, which is, as you said, with the slab allocator, is not so true. But with
Well,
the heap
let's consider
allocator,
the allocation logarithmic anyway.
yeah, exactly. And then you could assume, especially in a language like Java or C Sharp, which do so much allocation all over the place, you can assume that there was way more node in your heap that there's element in your array, right? Especially if you do, because let's say
Maybe.
you do a list, you will have for every element node. But all I want to say is that we can always assume that n is smaller than k, where k is the number of node, and then so rather than saying okay we have O of n plus log k, where k is a different number than n since it's the number of node
Okay.
in your heap. So let's say just n plus log n. So
Okay.
that's
Why not?
mostly like with a heap allocator, which is let's say a log k heap allocator, you have n plus log k. Where with a list, you have to do this new every time.
No, I understand. I understand what you're saying,
Yeah,
and I mean, purely theoretically, you'd be right.
yeah.
But
But
yeah,
I
your assumptions are not like they're not that they don't match real life.
but yeah, I didn't knew that you use a slab allocator, and I actually
Let,
look at the
let's
code right
even
now.
let's even completely forget about the allocator.
Hmm.
Even like for a user space application which has its own address space, the
Okay.
problem with that approach is that when n goes very high, you have lots of problems. Your copy might take a long time, so you might have spikes in your execution.
Hmm.
You risk fragmentation, especially if you do that for more than one type of object, which will be the case. Like no, like almost nothing
You
has
mean
just one
like
object
different
size.
array? Okay.
What?
You mean like different array of different object, because
Yes,
obviously you don't have the
yes.
an array. Oh well, okay. Yeah, I
And
got.
and then you risk wasting a lot of memory, potentially n times. And so when n
Yeah,
is very big, half your memory might
yeah,
just be
but that's
wasted.
what I wanted to say, because if you really think about it, just say a single link list, which is actually the worst list in some way. I mean, I can say if you don't do any removal, the single link list makes sense, but whenever you
No,
start
no.
doing removal,
Okay, okay. I see what you mean. Yeah, yeah. By the
and,
way, guys,
and
for the stream, the main difference between doubly and singly linked lists is exactly that: removal. If you want
yeah,
O1
exactly.
removal, you use a doubly linked list. Otherwise, you use a singly linked list.
And obviously, if you do a lot of removal, you might not go at all with an array, because that's not really suited to do that. But
Exactly.
let's say you don't do much removal,
No, but
and
that's where I mean, I understand your point, and that's where I know that there is no point going further because that's not my case.
yeah, but just about the memory space before, if you really think about it, let's say you have an array of pointer, which is, for instance, the case in Java, and the only reason you wouldn't do that in C is because it's more optimized. But or let's say you have an array of object that is less than 8 byte or less than 4 byte on 32 bits, whatever. That means the size of the array is roughly in the worst case, the size of the array is 2 times the number of element time 4, right? Or the number of byte of every
If you
of
use
each byte.
arrays, pointers, yeah, okay.
Yeah,
But if you
and
use
if
pointers,
you
then you have to allocate your objects somewhere else,
yeah,
which
but
kind of
in
defeat the
the case of
purpose.
yeah, exactly. But on the case of a classic implementation of the list, you have to allocate the node.
I
You have
disagree.
to allocate.
Well, a classic, okay, but as you can see here, it's not classic. It's
Yeah,
intrusive. It's by composition,
yeah,
and
exactly, and
actually,
that's way
lots of
better.
implementations, even in higher abstract, well, higher level languages, do it that way. You inherit
Mhm.
or you have an interface, something that allows you to directly have the node inside your object.
Yeah, but and that's why I wanted like to point out is that if you do a list, like there's really no reason to do it like the Java or the really like idiomatic oriented object way that you learn in school, where you have like this
I agree.
node of type T. But but because in that case the space because a single linked list you have to have the pointer to your element in Java especially where you only have the reference, but in C let's say you have to have in the node the object, and you have to also have a pointer to the next one,
Hmm.
and all the time the pointer will take the space as well, right? So if the element in your array are the same size as your pointer, the array will always take less space or equal to the list, because the list will always have the element plus the
Um,
pointer to
can
the
you
next.
repeat that?
Okay, so let's say, I know that's not exactly a good way, but like that's what you often see, and it's an list. For instance, in Java, you will see a list of reference, right? In some way, because there's you cannot
Hmm.
just copy the object. So that means every node will be roughly 8 bytes, and that means the
I disagree
size.
with that
Why that?
because a
Why do you?
node, in that case, a node is allocated, right?
Yeah.
So because it's allocated, there is overhead.
Mhm.
So it's not 8 bytes.
But
It's more than that.
even if it's allocated at the same time as the object, the node will still need to have a pointer to the next object. And I mean,
Okay.
when I say node, it could even be the object with inlining, like
Yeah. Let's assume
like
it's embedded,
okay, let's say it's embedded. So you will still have the pointer to the next object.
or even
And in this case,
let's also say there is a pref pointer to make it even worse.
okay, well, yeah,
Usually
like
they have a prev and next pointer. That's the common case. So
yeah, in the linked list, yeah,
yes,
for removal.
you
But
have
like
an
this,
ON overhead of space. Yes.
yeah, and that's the same as an array of pointer, which is obviously have the big problem of still having to allocate your object, right?
It's actually more.
Hmm?
It's more
But
because we have both prev and next, whereas
yeah,
the
with
array
the
just have
prev and
one
next,
pointer.
it will be more, yeah. But that's what I meant by like a single list. I really don't see why anyone will ever use that. Like
Be-
a double linked list, I can see why, especially in a case where you have a thread scenario, because if you have like a concurrency issue, it's it won't really affect the concurrency of your different thread to add a node, right? Where like if you have to reallocate the object, it's really problematic. But I was mostly because what I mostly do is reverse engineering on game and so on. And like for instance, in game, there's really not so much reason to use linked list because often you can do really good assumptions about the amount of item that you will have in your
yeah.
array.
Okay.
For instance, if you talk, okay, you have a game with entities, well, you can say, okay, I can make really good guesses about how many entities I will have in my array, and I can make even smarter guess. Let's say, okay, I'm in this zone, which is like a MMO, whatever. So I'm in a town where there's a lot of people, so I will create an array that is bigger at start, and especially on the client where like the memory is kind of infinite in some way. Like you will know that anyway, your texture will take way more. Like you
Hmm.
really don't care. You can make really large array and not care about that at all.
Agreed.
And so, but that's like I didn't see the point of like I can see that in the kernel is really different. Like there's not the same kind of worry. And I'm looking at your slab allocator, and this is roughly the kind of thing I did for storing entities. Actually, I had two array, one with well because I can see that you cache the like you create a first a big cache and then you just pull the spot
So
from there.
let's just go back to the original point, which was this library of modules
Mhm.
that were reusable and meant for like the page says. Um, does it say it? The page itself doesn't mention it, but I think the README. Well, there is the mention of microcontrollers for the shell, but it's specific for the shell. I don't think I talk about it in the README, do I? No. Okay, so basically, it's very generic. And
Mhm.
like you say, in the case of games, it's quite specific. Like you say, you make assumptions
Yeah,
on
exactly.
your usage patterns and data. That's not why I implemented those things in mind. Oh, not a very
Yeah,
good sentence,
but
but I mean, your point. So let's go back to your point. Why don't I have a dynamic array? because
Hmm.
I don't want to encourage people to just think in terms of contiguous memory and completely forget about fragmentation and overhead.
Yeah,
There is only one structure I'd like to add in there, which would be a lockless, dynamically resizable hash table. That's the only one
yeah,
that I think is missing. But a dynamic array, I don't think. It's easy to do yourself, easy enough
yeah.
compared
That's
to a linked
true.
list. Uh, so that's basically the reason. I think it's better for people to have that kind of code readily available rather than a dynamic array. Like I could make
Yeah,
a dynamic array, but honestly, it would be so simple,
yeah.
and I'm
That's
not
true.
even sure that it would. It could
But
make sense, like the free
there's
autos
an
queue. It could make sense, yes, but
there's another point that is that maybe in the kernel, I don't know because I never actually programmed kernel. You do less like iteration. For instance, in a game, you will do a lot of iteration on your data. So you will need like it will be really worth to have this contiguous memory and like a caching that
well,
your processor will cache the memory and you will be able to
so
iterate
I
faster
understand
on
what
it.
you say, and this is an argument that comes up very often, especially when I talk to game developers.
Hmm.
And I'm sorry, that's just not complete. That's not the
Yeah.
complete picture, and it's kind of wrong.
Why though?
People think that by just making memory contiguous, magically things are gonna work, and that's not true for a couple of reasons. First, you have to know how caches work to understand why it's not the case. So caches work by cache lines. So
Yeah.
first you have to understand how they work. Like virtually indexed or physically indexed is not the same thing.
Hmm.
So maybe because of that, your memory that you thought is contiguous is actually not from the point of view of the processor. That would be one thing. Luckily, most processors you are interested in, especially the PC, so x86, and newer ARM processors, the Cortex A basically, are all physically indexed. That's a good thing
Okay.
because our older ARM processors are virtually indexed, and other architectures are also virtually indexed. So that's one thing. The second thing is that if you're not careful about the architecture of your cache, you might have a lot of cache thrashing. Like, for example, if you have a big object, and that object is big enough that when you access the beginning and the end, it resolves to the same cache line, the same index, that's really not a good thing to
Yeah.
have. What else? You have also to take into account virtual memory. So I have referred to that paper in previous streams where uh, I forgot, Paul Henningkamp, I think, a FreeBSD developer, optimized an internet cache software. I don't remember exactly what, but something that handles a lot of data. And he made a specially crafted heap data structure that took into account virtual memory. So instead of making memory contiguous, he really packed all data that is related in the
Yeah.
same
The
page.
SOA ID, right? That's
Hmm?
like kind of the SOA ID, right? Like the
The
SOA structure, which pretty much if you have an array of structure rather than allowing rather than doing an array of structure, you do an array of every field in the structure more
So no, this would be
to
an array of
increase the
objects, and
cache.
then you pack your objects in a smart way inside your pages, and in a way that is like basically they're aligned to pages and cache lines both. Like
Yeah,
making things contiguous is not going to magically make things faster. Oh, there is also
yeah,
something to take into
definitely.
account. Today, almost every game has to do concurrency. So again, if
Yeah,
you're not careful about that, you're going to have cache misses all over the place. You might have false sharing, and you might have cache bouncing from one processor to the next. So
but one
just
thing
making
that you
memory contiguous is just it's a very small variable in order to make something just faster, you know.
well, it's a variable that won't make your thing magically faster, but you if you take in consideration and because as an really good example, I think it's typically this array of entities in a game. Like entities is a really big object in some way. They
Yeah.
will often be really large, and so rather than doing this array of entities, you take like there's a really small portion of the entities that you will use to render, right?
Yeah.
It will be like the position, maybe the type in some way,
And there
and
it makes sense to, yes,
and
allocate it
yeah,
in a structure that fits in a cache line contiguously. I agree.
Yeah, because that's really small. And you can, and that's one thing, for instance, that because I look at your talk about the oriented object,
Hmm.
and like one thing that you will often hear in the school that teacher will talk to you about virtual object, or you see really in those like idiomatic oriented object language, and I understand that it's irrelevant. It's not oriented object that require that in any way, but that's what you often see.
Yeah,
And like this is one terrible way. Like it will, if you really need performance, that will destroy your performance to
I
have
agree.
a
But
virtual object all
the
over the
reason why
place.
it's taught is because most of the time you don't really need that kind of performance.
Yeah, that's true. That I can see why
What you need
in
is
many way,
safety,
but
So
But
you need
what is funny is if you look, for instance, at Android Studio, because I had to use it recently, I was like, well, that need performance, that's for sure. Like I have a desktop and I couldn't run really smoothly Android Studio. It was so terrible. I was clicking on a thing to edit a text view, and it was like 2 second delay before I could actually write text in it.
Yeah, software is full
I
of
mean,
those cases where performance should have mattered to the developers. But that's more a scalability
yeah,
problem here rather than raw
yeah, that's true.
performance. One thing I wanted to say before we finish, if because I have to continue my work too, was about multiprocessing. Yes, one reason why you don't want to have contiguous memory in some cases is when you have a really partitioned use case, because well you might argue that you still want to have contiguous objects, and that would be true, but you would have to break your array if for example you have imagine an application that has one thread per processor, and you just use these threads as a way to emulate the host processors, and so the threads would be bound to specific processors. I've seen this kind of application like in
Yeah, often like a network.
deep packet inspection, for example.
Hmm.
In this case, you really want your structures to be local to your processor.
Yeah,
And so if you handle memory management yourself, you can't use the fact that the kernel knows exactly where memory comes from. And so Linux, for example, when Linux services memory allocation, is going to look at where the allocation is made. So what processor, what node if you're in the NUMA system. So that's really for bigger applications because we don't have NUMA yet on gaming machines, but uh, that's also another variable that you have to take into account. It's not just locality, from one data to the next. It's also all the path from memory to the processor and between the processors themselves. So that's I really want to emphasize, guys, that making data contiguous is just a very small variable in making software really efficient, especially today with all the complexity of caches and multiprocessors. So just be careful. It's good to think about that, but many times, unless you know that you really need it, it's not worth it. And in this
yeah.
case, using lists, despite all the defects that you mentioned, still remains the best case, because objects will be allocated more locally, because you will handle all the other cases like removal very well, quite efficiently. And
Yeah,
so yeah,
well,
having
that was really interesting.
sorry.
Yeah, that was really interesting talk, and I can see why. Like, and definitely, like performance often you can improve it because the amount of assumption that you can do on your data, for instance, that's a really
That's
big.
probably the best way to do it. But when you're doing a
Yeah,
generic system, it's quite hard.
yeah, yeah, exactly, and
And so my
that's
code is meant to be generic here. So that would be I think that's the best answer I can give you for your original
mm,
question.
yeah, kernel is really really different than a game, that's for sure.
So yeah, people
About
are asking questions, and I've been late. I have to answer
okay,
them now.
yeah, go ahead. I will quit.
So yeah, thanks for the talk. And guys, if we disagree, that's really okay. Um I like saying, like repeating it. Disagreeing is okay. Uh, you have your opinions. You can stick with them if you want. That's like no one has the real answer. That's it's all fine. Here we didn't disagree, but sometimes I have people I talk to who really disagree with me, and I really want to state that uh, it's only opinions about what we think, and it says nothing about the person themselves. Just to make it clear.
Yeah. Anyway, thank you. I continue to watch
Yeah,
your stream.
thanks.
Go ahead. It was really good.
User disconnected from your channel.
Well, that was a nice
Disconnected.
surprise. So just to close that, really close that, if you want a dynamic array structure, you can just send a patch. It's MIT licensed. I don't mind contributions, but I'm very, very, very picky on the coding style. Sorry. So let me take a look. Oh, and hello, yeah, hello, T-Blood. What is this? Yes, it's OpenBox and Xpanel. That's right. Oh, I can't look at this chat. It's too buggy. I have to resort to the old stuff that works. So we were somewhere here. Yeah. Okay, good. Information below the stream. Love these sort of conversations. Well, me too, actually. And it's quite rare that I get to speak with someone really technical who knows what he's talking about. And, well, I say rare. No, it's not that rare, but it's. I wish it happened more often. We all know that kernel development is hard compared to higher level development. I disagree. It's not that much harder. Actually, people think that's why I'm making this project, to show people that it's not much harder. Uh, the main constraint is that your stack is smaller. That's really all you have to think about, and that's it. How much math do you really need for kernel development? I would say almost none. What you really need is algorithmic complexity. So what we talked about, big O notation. So understanding what O1, ON, O log n means, that kind of stuff. There is no 3D, so you don't need linear algebra, trigonometry, etc. So what makes it hard to program kernel? That's it. It's not that hard. And to be really honest with you, what makes it hard is simply the fact that you will notice errors probably. Well, I mean, errors are going to have a bigger impact than in higher level applications. That's the only reason you affect more users, and the mistakes you make usually have more impact, like they're more dangerous. They may lead to security vulnerabilities. So basically, what's different is that the amount of expectations on the operating system is much higher than elsewhere. That's what makes it hard. You can write a crappy operating system. It's not difficult. You will have something that seems to work, that will work until some point where you have too many objects, or your memory is full and your system doesn't know how to deal with that kind of stuff. It's not that difficult. But yeah, the stack is smaller, so you basically cannot use recursion as much, and you have to basically you have to take care more about details. That's all. Details are like they have a higher importance, maybe. Yeah, there are slightly more details, and that's it. And I think that's all. So another question, I think. Can you lower stream quality? Yeah, answer that one. Sorry, Meshu, I tried, but unfortunately the setup I have now seems to be the best, so sorry about that. How isn't this issue for game developers simply solved by memory arenas and custom allocators? Sorry, I've not been around for the entire discussion, mostly AFK. How isn't this issue for game developers simply solved? Isn't this issue for game simply solved by memory arenas and custom allocators? Well, for the same reason he mentioned, because the problem is not the allocator itself. The problem is really the data structure, the overhead of the data structure, and the fact that it's not contiguous, so that you might, you definitely risk more cache misses if you're not careful. So it's really the data structure. The memory allocator doesn't know what kind of structure you have. It doesn't know the access patterns. So that's your job to take care of that. So basically, the problem is unique, almost unique for every kind of pattern and data structure that you need locally. Too few viewers interested in low-level stuff, I guess. In reference to what? Oh, yes, I see. Okay. Yeah, they removed. I had transcoding at some point and they removed it. Sorry. S list, are we talking? No, it was about dynamic arrays versus linked lists, whether they're singly or doubly linked. It was kind of awesome. I like that. Well, I'm glad you liked. I liked it too. I actually forgot, but send you a toy example on TS. There is few dumb stuff there here for a reason not good. Oh, I closed it. Shit. Um, yeah, no, I don't think it locks the chat, but I'll take a look after. I really need to go back to coding, but you can just send my email address is on the website somewhere in about, I think, so it's easy to find. And if not, it's in the Git logs, so really easy to find. Hello, Slayer Darth. If I didn't told you already, I'm interested in low-level stuff. I have you know. Yes, more involved on the web front though, so I'm still learning a lot about low-level programming. Okay, student tuning in, interested in ARM VHDL programming. Okay. That's quite low level, at least for me. Oh, thanks for the link. Okay. So EE for electrical or electronics engineer, maybe, probably. So ARM programming. Why are you interested specifically in ARM programming? Actually, I used to be interested in ARM programming, and honestly, now I'm not. I'm interested in making my software run on ARM, but the only reason is because ARM is uh, a major player. I like there are lots of hardware running ARM, and uh, that hardware is great. But ARM itself, it's very difficult for an operating system designer, well, developer really, to cope with all the diversity. Really difficult. They made efforts. They're aware of the problem, and I think they know that they made bad decisions in the past that they could have avoided only if they agreed to copy what Intel did. Because from my point of view, Intel made almost all the right decisions. It's impressive. Caching, virtual memory, the instruction set. Like ARM used to stand for Advanced RISC Machines after Acorn RISC Machines, and now it's just ARM because it's not RISC anymore, because RISC is not considered to be the right approach today, and it's not. And Intel has proved that. So ARM itself, I don't understand why it would be appealing itself, without the rest, without the community, without the environment, which is great. They recognize, and that's something I really like about the ARM company and the people in it. They really recognize that what makes ARM great is what they call their partners, the ecosystem. I don't remember the exact word, but basically they recognize that them alone, who cares? They're not that great. But the fact that they work really well with others is a really good thing. And it also helps making stuff more portable, especially, for example, um, virtualization is very specific to the x86. So by having QEMU and KVM on ARM2, it really improves code quality by making it more portable and forcing people to come up with the right abstractions. Game devs do their stuff either with SOA or AOS. It's a bandwidth problem most of the time, even when with cache involved. Yes, I agree with that. Completely agree with that. But that also means that you have to reduce the need to move memory. And that's why, for example, knowing about virtual memory is very important, because if you have a data structure that takes into account virtual memory, you can come up with a lot less page swapping. So not the kind of swapping that people are used to when they hear that, which is basically write stuff to the disk, but swapping by maybe it's not the right word, but paging in, paging out, like just flushing pages and later reloading them, not even writing them back, because mostly they're read-only, they're textures or I don't know what. Um, and so grouping according to the virtual memory page is also very important, and many people it's something that many people just don't know about. Virtual memory today seems to be a very dark corner of computing that only operating system developers care about, and not even like only a couple of them. because all modern systems have the right abstractions, so that people don't care about virtual memory, just can ignore it. Oh, I have a quick story. Oh, wait. So entity management in games is a problem that's been complicated, I guess, mostly because of the object-oriented world models in recent C++, let's say WORDs. I don't know if recent C++ is actually a problem with that, but maybe. It's true that one reason that I don't like C++ is because, unlike C, I have a hard time knowing how the code is going to look like and how memory is going to be laid out. That's right. But yeah, maybe you're right. I don't know. I don't know enough to know what you can actually do with those abstractions. But those abstractions again are meant for safety. At the same time, there is a paradox because I agree. Yeah, they're meant for safety, but at the same time, you have things like uh, R value references, which are meant for performance, so that you don't have to create temporary variables, um, and you can just directly pass your R values around. So it would be quite weird to have one part that is for safety, the other for performance, that they don't combine to give you the most of what you should have. Basically, that if you want performance, you are hindered by the safety side and the other way around too. For most of my LAMP stack sites, running a local host meant to use a dev domain. A recent Chrome commit has since caused Chrome to detect dev as GTLD, so now any HTTP requests to my dev sites are redirected to HTTPS. Guess now my days of dev domains for my local sites are over now. That's weird. Are you sure it's Chrome? It might just be that there is a dev domain. I don't know, that's weird. For me, the browser shouldn't do that, but maybe they do. It just happened to one of my localhost sites this morning, and I was wondering if it maybe worked. Uh-huh. I'm off to watch your VODs. Okay, have fun. They're quite long. They're really for the devoted ones. You know, those who are really interested in spending the time to, well, to learn not that much, to be honest. You'll learn probably more by reading the code once it's commented correctly, which is not the case yet, as you can see. So, destruction. Wake up is fine now. It's fixed. Okay, so in exit we do wake up the joiner if we have one. So joiner is synchronized with interrupt and preemption. Oh, by the way, preemption is enabled here, so we want to disable it. Like this. So we disable preemption, we disable interrupts, we make sure the thread is running, we set it to dead. We wake up the joiner if there is one, and then we schedule with our new state. Okay, and all this is in the critical section that is created by these two things here. Okay. And so our thread is going to be dead, simply put. So how could we saw this? How could we see that? Is there a point to see that? We can directly implement the code, I think. Let's implement join and then we'll have some test. I'm on macOS at work. Otherwise it's Firefox or Safari. But you can have Firefox on macOS too, right? Only use links. Yeah, only use W3M, like W3M. This is what Google looks like. Oh shit. Hey, full screen, full screen. It's the 80s, right? Well, no, actually the 90s we have colors. And a big screen. Links is good too. Apologizes for bike shedding on the stream. That's okay, that's perfectly okay. Like Minitel. Yeah, I've been taught in by some people that my desktop environment and my consoles look like this old French stuff that came about around the same time as the internet, but was much worse. Right, so how do we implement thread join? We have the target thread. That thread must exist. So yeah, it probably does exist because it cannot be destroyed by anything else, so that should be fine. If it's not fine, it's, undefined behavior. So basically, it's the user's fault, not mine. We probably want to create a critical section as soon as possible. And here we do need deflags. Actually, you can just do that here. We don't need deflags here because we never restore interrupts. Interrupts are a thread-specific property. So basically, when we schedule here, the interrupts of the thread that is next scheduled are going to be restored. So we don't need to do anything for exit, but here, because join is likely to continue running, very likely actually, we do need deflags. Okay, disable preemption first. In that order, okay. So here we are in a critical section, which means that we have the processor for ourselves, which means that nothing else can happen. No interrupt, no other thread might run. So the complete state of the system is stable, which means that we are allowed to look at anything. And we want to check the state of the thread. So the thread may either be dead or not dead. And setting dead and waking up is done in a critical section, so it's atomic, which means that if the thread is not dead, the joiner cannot be awakened. And if the thread is dead, the joiner has been awakened. So there is no problem with that. Interrupt thread specific, wouldn't that kind of ruin the point of interrupts? Yes, you have misunderstood. What I mean by that is that the interrupt flag is thread specific. So basically the ability to receive or not interrupts is thread specific. So when you switch to another thread, it is the flag of that thread which is restored. And that's very important because that's what allows efficient scheduling. That's the difference between preemption and interrupts. And the confusion comes from the past, because in the past, interrupts were used to control preemption. No, it's really okay to be confused about that. I have been confused about it for years. Like around 2005, 2006, when I first write the first serious systems I have written, it was a seriously confusing thing for me because I thought interrupts would be global as well. And so when I tried to come up with a decent scheduling algorithm, it was very difficult to achieve. And so I had to come up with this realization that interrupts are thread specific, thread local, like preemption, by the way. Preemption can be made like here. The preemption counter is literally in the thread structure, so it is thread local. But when you have a single processor, you can also have the preemption level to be a global variable. That's okay. What could be the possible reasons for a seg fault on a valid pointer on ARM? On Linux? I don't know. Can you check DM ESG and pass what the kernel tells you? On Darwin, oh. I don't know Darwin that well. I know the Mac microkernel, but I don't know the ARM part of it. Honestly, I don't know. Yes, Darwin works on ARM, yes. That means iOS, yes. Honestly, no. It's I would imagine a SIG bus, sorry, but a seg fault, so a SIG seg v. A SIG seg v is just because you have an invalid memory access. So can you check if it's aligned or not? But again, that would be SIGBUS. The problem with that is that I don't know the details of Darwin. Maybe Darwin doesn't convert processor exceptions correctly, and some of them are translated into segfaults instead of SIGBUS. But check that your access is aligned. Check that it doesn't cross a boundary, like a page boundary, so you think it's mapped where actually the end of what you're accessing is not. Bad access, current valid address, which would suggest the pointer is pointing to an invalid address. Let's take a look at this. It's not the same kernel, but it's very close. It hasn't changed much. So, exceptions, I suppose. I don't think I will have them here. Okay, quick look, very quick look. Thank you for the stream. I'll tune out early. Have fun, everyone. Take it easy. Yeah. Thanks. Thanks for watching, localhoster. According to the debugger, it's mapped, and it's mapped with the right permissions. Could not access memory, exception, trap, but this is only for i3x6, right? So I can't really tell you. I don't think I have XNU on this machine. Nope, I don't. So I would assume it's that, But really, I don't know. You have to check that yourself. I would check in the source code. You can download XNU. XNU. Okay, so I have my critical section here. What's the state of the target thread? The target thread is either dead or not dead. So if it's dead, I can release it immediately. And if it's not dead, I have to wait. And then I can destroy it. So it's actually while, because we're going to sleep, so we might have spurious wake-ups, so we loop. And we need that. Okay, so at the same time, sleep here already makes the check that the preemption level is okay, and that it's strictly 1, so this means that here preemption must not be enabled, which is alright. Sorry, preemption must be enabled when calling join, which is okay, because it's actually normal, expected, because join might wait, so preemption must be enabled in order to wait. Okay, so thread sleep has no argument. Okay, and so here, if we come out of this, it means that in the function right above, this happened. If the thread is dead, we have been awakened, right? And if it was already dead in the beginning, we don't need to sleep. Okay, so now we just have to destroy the thread. So thread destroy, I don't know what it does yet. That's okay. And I guess that's it. Oh, we have to restore. Interrupts and preemption. Okay, and then we can destroy the thread outside the critical section, because it might be a long operation involving memory allocation, well, memory release, but that's basically the same constraints. So according to the debugger, it's mapped. There's one problem with this line of debugging, which is I have no way of running a kernel debugger on an iPad. Yeah, okay. Yeah, you're looking at the right source code. But also it's ARM64, and ARM64 is quite new, so I wouldn't be surprised if it had such bugs. You have to realize that XNU is a very crappy kernel internally. And so I know that because I have worked, like you've seen, I have worked on GNU/Mac, and I have looked at XNU to see how they solved some problems that we had. And so I looked at the code, and the virtual memory code is a monster, an abomination that just grew out of bad code. So it was bad code initially, and it got worse by stacking conditions and indentation levels and loops and in functions that are like hundreds of lines long. It's not too new for Apple to deprecate 32-bit ARM. 32-bit ARM is deprecated for Apple? What the hell? Well, it makes sense because, yeah, like I said, the code is crap, and they probably don't want to maintain that crap for so long, so they probably want their team to focus on just one thing. Makes sense. Can't submit 32 apps anymore. Yeah, that's another story. That doesn't mean the system is deprecated. But it's a strong step. It just means that they just want one version of the apps because it makes everything simpler, and they're right about that. But the system itself, it's another thing. So let's implement thread destroy. It's going to be a static function that I'm going to write here. Thread destroy. So we know the thread isn't running anymore. Okay. We know because it's dead. So assert that thread is dead. Okay. Yeah, okay. So what do we need to do? We need to release the stack and the thread. Any other resource that we might need? Normally init does no allocation, no resource allocation at all. So it just builds the stack and sets the fields, but that's all. Okay. What else? Run add should be a simple list insert. Yeah, and a set yield, but that's just a flag. Okay. So we just need to do those two frees and we're good. So stack, let's take a look at the data structure here. Okay, it's that one. Okay. And basically that's it. So it's very, very simple to write. Just look at the diff. We basically added a state. We added a field here that I forgot to initialize. I'll have to do that. I forgot to write is dead, but very simple. So I made thread main call thread exit implicitly. So implicitly from the point of view of the thread, but explicitly here. And so I have those three functions. Destroy just freeze. Exit is probably the more complicated one. Yeah. So disable, like it enters a critical section, it sets the state to dead, it wakes up a joiner if any, and then it schedules with its new state. I have to make sure that this function correctly handles this new state. It should, but I have to make to check that. And join here just enters a critical section, waits for the thread to become dead, and when it is, destroys it. It's really simple. And here I moved an assertion in the critical section, nothing major. And I handle the case where the thread that we want to wake up is null. Okay, very good. So let's initialize joiner. Joiner is after preempt level. And it's null. Okay. Then we need isDead. And I'm not too happy with this ordering. Let's it's not very scalable. Could have just copied and replace. So let's move that here. Is running, set running. Is sleeping, set sleeping. And is dead, set dead. Okay. Oh, music, sorry guys. Sorry for myself too. I think it was 27.4 if I remember correctly, and like this. By the way, if you don't know her, Katrina McKay is a Scottish harpist, and the Scottish harp is actually a very special harp, so if you're interested in that kind of music, you have her name. I said that I needed to check whether RunQ schedule was correctly able to handle that new state, and you can see here that it's not. I use is sleeping when I should be using not running. By the way, let's check all the uses of is sleeping. Wake up, so thread is sleeping, set running, okay. We should make sure that we never wake up a dead thread. I don't suppose you have a Last.fm. No, I don't. I'm old-fashioned. All my music is local. Well, it's on my server, so there is a remote file system, but it's local because it's, you know, my systems. And the reason I keep doing things this way is because I don't like the tools, really. They're heavy, they're not easy accessible, they have ads, or you use an ad blocker or things. It's annoying for me. It's just annoying. Like, look at this. This is my music player. You can't really make it more simple than that. Well, it's more complicated than you think because it has, you know, hotkeys and actually quite a bunch of features. But I really like it this way. And you can script it, and you can even like I can quit it, and it just runs in the background. You can reattach. Just so convenient. Some people think that Unix is not friendly. I can't agree. Okay, just for tracking, if you use MPD, I'm pretty sure it's available there too. What's MPD? I actually don't know. I'm using music on console. So sleeping here is fine. This is the only use of sleeping. So what I'm going to do is that I'm going to remove it because I don't want users to check whether the thread is sleeping or not, just whether it's running or not. And so here I'm gonna do this. If thread is not running, and then we assert it's also not dead. Right? Otherwise it's running, so we don't care too much about the state. Let's write a test code using just the interface that we have here. Okay. So how am I going to do this? It's actually very simple. I'm going to write two functions. I can remove all this. Okay, so this is going to be test1, and I'm going to have test2. Music player daemon, highly customizable backend music player, then you add a front end for each widget, like PC, NCM. Okay, well, it's interesting. I'm gonna look into it. I agree that music on console is really old. Like, how old is it actually? It's so old. 2002, yeah. It's not as old as I thought, but I think I've been using it since 2003 or something. I don't even remember. And that's where you realize that you're getting old. Okay, so I want to create 2 threads, one with test 1, another with test 2. Okay, and then we enable the scheduler, great. So this is test 2. Test 2 is going to need a handle on test 1, which we will pass this way. So let's copy those statics here, remove static. Whoops, I remove struct. Okay, and so here I pass thread 1. Okay, so thread 1 is going to be this. Thread join. Okay, and then here we ignore the argument, we ignore that. The only thing we're gonna do is actually let's just print the name. Like, do we? No, we don't really need to print the name. Let's just print exit. And actually, it's just use a space. No need for a new line. Okay. Okay, it's like CMS. I don't know what CMS is. Mostly terminal based, but you also get some higher level frontend, so that's great. That's one weakness of Mock, that the frontend is a bit poor. Poor in the sense that it should be separated into a library and a real frontend program. Maybe it is, I don't even know. Like, let's actually test. Because I'm talking, but yeah, there's so many libraries. Yeah, apparently it's not. That's usually a mistake. You want to create a library for your engine so that you can have multiple front ends easily. Like Transmission has, for example. Transmission is a great tool in this. Like, the way its architecture is quite good. Really good. A very good example. So one thread exits and the other joins it. So let's take a look at all the compilation mistakes that we're gonna solve. None. How great is that? And we do have an assertion. Okay. 482. Let's see. Ah, stupid me. I handled the case where the thread is null and forgot to remove the assertion. Okay, it's not working. What should I do? Let's take a look at the processor first. The virtual machine... Oh, I'm not sorting by the right column. The virtual machine is not running, so it's running idle. Okay. Which is weird. So we had an assertion because a thread was null, which means that we have exit called before join, right? Because then it tried to call wakeup with a null joiner. Oh, stupid me, of course. Here, the joiner has to declare itself. There. Much better. Let's make sure that we actually destroy the thread. Excellent. So that's it. Destruction done. Gonna check the diff, see what's missing. Okay, so right now with the code I have, this is what it looks like, right? Okay, perfect. I could actually have new lines. So is dead, set dead, is running, okay, to do destruction that's done, joiner, the small 3 functions that I added, and a couple of very minor modifications. Okay, pushed. So that part is done. So next, I'm going to implement mutexes, and if I have time, I'll implement condition variables. Again, it's going to be very, very super simple, like really simple. Let's take some very simple code as a starting point, like your driver. Add to Git so that you don't lose your work by accident. Okay. Do we need to set up anything for mutexes? I don't think so. We might, like with more complicated implementations that require some global state, yeah, but here that's not the case, so we can just ignore that. Let's create our object. We want our object in the header because we want users to be able to allocate it on the stack or inside other structures, so it needs to be public, at least in the public header. What you could do, by the way, that's something I'm not showing in this project, but in X15, this is how, for example, I have private objects. So in the header, oh yes, this one is even more complicated because there are multiple implementations. Let's take something simpler, like scalable references maybe? Right, so this file is the public header. And in the public header, I provide the types. But you can see that they're not defined, they're just declared. These are forward declarations. But I still want people to be able to use those types on stacks and inside other structures. So what I do then is that I have an _i header, which provides the content of the structures. And then in the coding style, in the coding rules, it's explicitly mentioned that those headers are for inline stuff or for implementation stuff or internal stuff, you know. So basically, when something is there, the user should not rely on it. The only thing the user can rely on is the public header, the public interface. So the API basically, and this would not be the API, and this could change without too much trouble, but this only works if you recompile. This is only the API, right? If you change your private header, you break the API. So it's good inside projects, but not across them. And for example, what C libraries do to make mutexes work on over time is that the mutex contains some space, some arbitrary state space, larger than it needs, so that when the implementation changes, the internal content of the mutex can change, but the size of the mutex doesn't. So it has been reserved in the past, and it keeps working this way, precisely because of binary compatibility requirements, which I don't have here. Right, so basically what's a mutex? a mutex is a list of threads waiting for a critical section to be exited. So basically for the previous owner of a critical section to give ownership. It's not going to really be giving ownership because that's a complicated thing that I don't need. Just waking up the next thread is going to be good enough. So we need a list. Alright, it's in library. Threads, which are basically waiters. What else do we need? We need to know if the mutex is actually held or not. So we need a boolean that I'm going to use here. So locked, for example, or acquired or owned. Alright, now the interface is going to be very simple. We have mutex init. We have lock, try lock for the non-blocking version, and unlock. Okay. For now, that's the only thing we're gonna implement, and we'll see if we need more than that or not. So we know we need std bool, the rest can go away. We know we need lists, and obviously we know that we need the mutex header, which is local, so I'm going to use quotes instead. Yeah, okay. Probably faster ways to do this, but it's a 10 seconds difference. std bool greater than bool. std bool provides the bool type in C99 and C11. Okay, so initialization, very simple. We have an empty list of threads, and it's not locked. Very simple. Locking. So, locking requires a critical section. So we are using a critical section of one type to implement critical sections of another type here. This is something that you need to realize. That's one major difference, for example, between, if you're used to Linux, between spin locks and mutexes. Spin locks are usually considered lightweight because in the absence of contention, they're like just changing a counter for preemption and an atomic operation on some internal word. And then, because preemption is disabled, you don't have the overhead of context switching and sleeping and waking up, which is expensive, especially on multiprocessor machines. So disabling preemption is the most lightweight and the fastest way to do things. So for example, if you're in a kernel and for example, you have priority inversion problems, you may want to disable preemption instead of using mutexes in those cases. Basically, when your critical section is lighter than the critical section required to implement locking or unlocking a mutex, don't use a mutex, right? Use mutex for expensive critical sections. Alright, so we need the CPU too, because we need to disable, like, do we need to disable intruts? No, we don't. And the reason we don't is because we cannot use mutexes from intrutt handlers. Okay. So here we check whether our mutex is locked. Okay, and we're going to optimize for the absence of contention, which means that we want the likely case to be that the mutex is not locked. Okay. At the same time, do I want to use likely and unlikely? I have those macros here that are the same as the Linux kernel, which are implemented using a built-in from the GCC compiler. Could be an example of doing that. That's a good way. That's a good use case. A good way to show people that this stuff exists and how to use it. So let's use unlikely instead. Okay. So if the mutex is locked, basically we sleep until it's not locked. So we could implement it with a while. So what we're going to do is that the current thread, so the caller, appends itself to the list of threads on the mutex and sleeps until locked is false. So we need if here. Okay, we're going to implement a FIFO policy, which means that the first thread that locks the mutex with contention, so attempts to lock the mutex but fails because the mutex is already held, is going to be the first one to be awakened, right? First in, first out. So. Threads, okay. And we want to insert ourself. Do we need anything else? Probably not. We can just write it here. Thread self. No. Wait. So we don't want to insert threads directly because that would mean allocating the nodes, well, the node pointers in the thread structure itself, which is not needed here because we can directly use the stack for that. But this also means that we need a temporary object on the stack to get the thread pointer from this object. So we're going to call that mutex waiter, and in there we're gonna have a list node, and then we're gonna have the thread that we want to find from the structure. Okay. Okay. Alright, so the caller is now in the list of threads. And so now I want to loop until I acquire the mutex. But because I have tested that the mutex is already locked, I don't need to test it again, which means I'm going to use a do while instead. And we keep doing that as long as the mutex is locked. Okay, so thread sleep here has no argument. Again, you can see how thread sleep requires preemption to be disabled when it's called, so that everything here is atomically locked, right? So that, for example, when unlock is called, it will disable preemption too, which will completely exclude this whole code from running at the same time. And so when the caller of lock here sleeps, then preemption will be re-enabled, allowing unlock to run. And this is how you implement this this atomic coupling between threads and mutexes. I talked about that last time, but I'd like to show you again how it's done. Here, see, you lock. Here you have your while loop to guard against spurious wake-ups. Then you have your sleep. So sleep here has arguments. It has a condition variable in mutex. But sleeping at a low level doesn't need any argument because the only state that is required is disabling preemption. And disabling preemption here is not passed as an argument. It's some thread local state, accessible at any point from the thread. But it's really the same thing with just a bit more arguments, like you can ignore the timeout. And here there's coupling between the two. And the coupling between the two is not obvious here, but it's really the same thing. And it will probably be more obvious when the unlock implementation is done. And then obviously we unlock here. Anything else to do? Yes, we actually have to acquire the mutex. Okay, so we could also set an owner here to make sure that the mutex is always unlocked by the thread that owns it. We could do that, but it would make the mutex slightly less efficient. Is that a problem? Let's actually do it. Okay, so here we have the owner. Okay, and when we arrive here, we make the mutex locked and we set ourselves as the owner, which means that we will want this structure here, or this pointer outside, and also this call here, outside the critical section. Okay, that's good. The try lock. So the try lock is going to be much simpler to implement. And we could actually call try lock from mutex lock. We could do that. Yeah, we probably want to do that, we'll see. I don't know, it's more complicated. Oops. So it's basically this if here. We expect the mutex to be unlocked, right? Also we need to return whether the thread is actually locked or not, so we're going to return an error. What kind of errors do we have? Yeah, we want busy. I think busy is the code used here. So trilog busy. Okay, yeah. That's what people are going to expect. Tuning out, have a great stream. Thanks. It's already 11 p.m. Wow. But thanks for staying that long, guys. I'm quite impressed at your endurance, really. Your is endurance stamina, I guess, is the right word. Because you know, this is programming. This is not even video games. It's I guess it's a little more involving, especially when there isn't much interaction. And since we talked earlier with oh shit, I have such a bad memory. Redoff? Yeah, Redoff. We haven't talked that much. So if you guys want to talk about things, you know, just go ahead. Anything technical. But it's interesting. Yeah, it is interesting, but not for many people, you know. That's why there are 13 of you on the, I think 13, yeah. Sometimes it's 13, sometimes it's 25, that's weird. Anyway, we're not many people, you know. And even if it's only a few people, even those people, I know I'm one of them, I watch other streams, so I know that it's often quite difficult to, you know, get really interested and involved and stay long in a programming stream. My turn 2 long sleep. Yeah, I'm also exhausted, guys. But as long as I'm doing this, I'll be awake. So I guess I can keep doing that a couple of hours, but I'll try to end at midnight. Midnight at most would be fine. Like after the condition variables, it would be great. Maybe I won't even do the condition variables. Yeah, maybe not. We'll see. It's really easy. It's almost the same thing as mutexes, but with a little quirk. Okay, so basically we want to lock the mutex if it's unlocked. So let's use unlikely. I like unlikely. I like the likely path to be at indentation level 1. Bye Bloot, yeah. Thank you too for staying that long again. So if it's locked, we want to return errors, well, 1 at least. Let's see. Whoops. Okay. So one thing I don't like here is the duplication of that stuff here. So either we write a small function just for that, or we use try-lock from block. But I'm not sure we can really do that, because then it would duplicate the check here, which we really don't want to. So I guess just a small function for this should do. Oh, actually thread is fine. Right, so we assert that the thread is not locked, the mutex is not locked. And also that there is no owner, right? Okay. Early refactoring, great practice. Something you should really train yourself to make a reflex of. And I didn't go as far as I could, like for example, even accessing this could be made an accessor, but I mean there are so few occurrences that pragmatically it's not really, doesn't bring any gain for such little code. Okay, now the unlock. So first things first, we make sure that the mutex is locked. We make sure that the owner is the current thread. Okay. Once this is done, we need to enter a critical section by disabling preemption. Okay. Oh, by the way, we need to make those checks while preemption is disabled, obviously. Although it's not really necessary, because normally no other thread is allowed to change that. Only the owner can change them, but just because of the barriers that are provided by these functions, I'd like to have those assertions inside. So yeah, when I say barriers, what I mean is preempt, disable, for example, void. I mean precisely these things here. And actually I'm going to reorder them. Yeah, see here? Disable is like basically like acquire or lock. So you do some stuff and then you have a barrier, which clearly separates the code that is responsible for entering the critical section from the critical section itself. This is a compiler barrier, so it prevents the compiler from reordering the code. It works on a single processor, but when you have multiple processors you have to use memory barriers as well, so that's another story. And here, when enabling preemption is the same, you see the barrier, so basically your critical section is inside, and then you quit, you exit your critical section with that here. And this barrier completely prevents code from leaking out of the critical section. So this is something I really want to have here for my assertions. But normally it should be safe to do them outside. Okay, so the owner is right, the locked state is right, so what we do now is that we unlock it. So we could use the reverse of set owner, which would be clear owner. And so clear owner actually will have the two assertions here. Maybe not actually. Yeah, it can. It could, but then it has to call thread self. That's not great. Although we could make that into an assertion, which means that when we have no assertions, the code is compiled out, and so there is no performance penalty doing this. Okay, so let's move those assertions. So for example, when I mentioned giving ownership, what I refer to is instead of setting the owner to null, we could set the owner to the next thread in the list of threads here. And this would really be giving ownership. But this is complicated because here, when locking, you wouldn't just look at whether the mutex is locked or not. You would also need to check no, actually the mutex would stay locked, but then the unlock operation we need to see if there is a next thread, and lock, well, keep locked or unlock whether we do have an extra or not. It's not that complicated. We could do it. But let's keep it simple. It's a really minor optimization that is not needed, so okay, no owner anymore, the mutex is unlocked, so now what we need to do is wake up the next thread. So we need to check whether the list is empty or not. Threads, okay, so not empty, because if it's empty we don't have anything to do. And if it's not empty, we grab thread self. Actually, it's not thread self anymore. Okay, so thread would be the first entry. Oh, I forgot to save that. Oh yes, I forgot to save. Okay. So list first entry. Actually, wait. How do I insert the threads? I insert them at the tail. So yeah, I want them. I want to pop them out from the head. So, okay. First entry, we need the list, we need the type, and we need the member. So the type would be a thread, and the member, oh no, it's a mutex waiter. Okay. The structure which is here, this one. Okay, and the node is called node. Okay. So we need a waiter pointer here. Okay, and so then we do, for example, we want to wake it up. So mutex waiter wake up. Okay, so we have to write mutex waiter init and wake up. Okay. Okay, we want a thread. Makes sense. And here we just want to wake up. And so wake up. Okay, we'll just have the thread. Okay, so that's basically the implementation. We have critical sections. When we lock, we check whether the mutex is locked or not, and if it's locked, which is unlikely, we insert a waiter in the list of threads. So that should actually be called waiters to avoid confusion. Okay, it's always used like this. So let's just replace it completely, and we don't have any problems with the number of columns. Okay. So we check whether the mutex is contended, in which case we insert a waiter referencing the current thread, and we sleep as long as the mutex is locked. Okay. When it's not, so either because it wasn't locked or because it became unlocked, we become the new owner of the mutex. Try lock basically does the same thing, except it doesn't wait if there is contention, and unlock clears the current thread as the owner, and if the list of waiters is not empty, it grabs the first one and wake it up. And you can really see that I try to write the code in a way that makes it almost, natural language. What I just said is quite close to what's actually written in the code. And this, what I've just said, is what I call explicit programming in the documentation of X15. In the coding style here, I mentioned explicit programming, and that's exactly it. Basically, write your code in a way that makes it say what it does in a almost natural language. So this also means that personally, I really don't like syntax. And C++, for example, is full of syntax with angle brackets, double columns, multiple uses of different, like all those syntactic symbols. For me, who's looking for a very natural way to write stuff, it's really, really annoying, because then you have to remember more stuff that you don't really need. That is a constraint enforced by the language. And one reason I like C is because the syntax is quite light. There's this annoying thing. I agree that the semicolon is a bit annoying, but you get used to it. What I really don't like is the arrow. Like, the point or the arrow should be the same thing, and the compiler should be able to see that if it's a pointer, then you dereference it, and if it's not a pointer, then just apply an offset like the dot would. That would be great. That would simplify the syntax even more. No errors? That's weird. I don't have a test. Okay. So this is my API, and I want to test mutexes. So what could I do to test mutexes? I could increment a counter. Like, let's try to implement a counter without mutexes and with mutexes, but how could we check that we don't have a problem? We could implement a queue, but we don't have condition variables yet. No, the only thing we can do is have 2 or more threads running, accessing some shared memory, modifying that shared memory, and making sure that the modified memory is valid. So basically, we read, modify, write, read again, make sure that the value is the same we have just written. Okay, we only need one function for this. I don't need to make the thread global, but I need to make the mutex and the shared memory global. And I need to actually include it. It's temporary, so I'm going to make it a part. Text, yeah, mutex, okay. We want to initialize the mutex before we use it. Okay. And so test here is an infinite loop, locking the mutex, unlocking it, and between the two, let's say that we have a variable, a counter, that we want to initialize to. Well, actually it's global, so it's already 0. Alright, so what we want to do is increment it. Now, the problem I have with this is that, look, if I want to check it, let's actually have a cache value. inside it counter. So we read it. Whoa. Okay. We increment it. That's really what the compiler is going to generate. That's the code is going to generate. Read, load from memory, increment, store to memory. The problem is if I do it this way, the compiler is going to optimize. So in order to prevent optimization, I could use volatile. So this would become an access, this would become an access, and this would become an access. I could do that. I could have a barrier which basically has the same effect, for example, like this. By doing this, I force the compiler to generate all those instructions before the barrier and all those ones after the barrier, and the code cannot leak across the barrier. So the compiler would be forced to generate instructions to reload the test counter variable here. And this one too, by the way, but this one is local, so we have a guarantee that it can't change. Okay, so it's a mutex, which means that we are allowed to yield the processor, right? So let's do just that. Thread yield. It's this function here. So basically we give the processor to another thread, and that other thread is going to do the same thing. So actually we don't want to yield here, we want to yield here. After, like when in the middle of modifying the counter, so that we give a chance to another thread to run and change the counter. My goal here is to trigger this panic, to make sure that the mutex actually protects the shared memory. Unused arg, yeah, it is unused. And by the way, we don't need to pass thread 1 here. Okay, so we have two threads now. We could have like an array of threads, or rather I could have a loop of thread creation instead of manually creating two threads, but let's test with that. It should already work. So we have a counter, okay, then we have thread yield. Let's take a look at thread yield. Yeah, it has a barrier, great. Thread yield should act as a barrier, at least if it schedules. And it should schedule. It should schedule because preemption is enabled here. So we reach that code, and when giving the processor to another thread, there should be an implicit barrier, which is the case here in those functions, and even in that one, I think. All right, so we read it, we modify it, we write it, and here what should happen is that another thread has read the counter and incremented and should have the same value here. So we should write the value twice. But that's not the test I want to do actually. Or is... no, it's... oh no, that's not true. Both threads are going to write the same value and going to see that the value hasn't changed. So the test is going to pass. That's not what I want. I want to make sure that the value is incrementally, or is incremented monotonically. Yeah, that's it. And because it's late, and I'm exhausted and not generally good at this, it's not obvious to me. Basically, I want to trigger the error. I want both threads to access the memory at the same time, and the counter will not be incremented correctly. That's what I want to do. So what I should do instead is cache the original value and make sure that the increment is what I read plus 1, right? like this. So here I read a value, and here I change it, and so the value I have here should be the previous one plus 1. And so what I expect is that by having this yield call here, I force another thread to do the same thing. Then both are going to increment this counter. And because it's a single processor, yeah, it will work most of the time, and sometimes it may not work. And so I should have this case, I should have this condition once in a while. But with a mutex, I should never have a problem. Mutex init. Really? Undefined reference to mutex init. Whoa. So wait, I include mutex h. The function is correctly called mutex init, no typo. Oh, stupid me. I forgot to add it into the make file. Okay, that makes more sense. So, 60. Yeah, we don't have a cert, that's right. We do have null, right? Yes, so we need stddev2. What else? 93. Oh yes, I have this one is a structure on the stack, so it's a dot instead of an arrow. That's annoying. Oh wait, it's actually this one. Thread and declared 116. Because that would be thread self. Okay, control reaches end of non-void function on line 120. That's right. Yeah, I was. Invalid counter value. So yeah, we have the panic. And now, with mutexes, we should never have that panic. Okay. Let's make sure that the code actually runs by using GCC, connecting to the virtual machine, and printing test counter. It's only 2. That's not great. Something's wrong. Something is really wrong. So let's see. I'm going to disable optimizations. I should actually add a comment here to mention the different optimization levels. Okay, we have a better stack trace. So we are in mutex unlock, and clear owner. It's always mutex unlock, right? No, oh wait. No, it's locked now, but maybe it's the other thread. Oh, okay. That's weird. Yeah, it's a bit weird. It's like too weird. It seems to work fine here, but not with optimizations. Yeah. Not good, so what do we need to change? It's probably not here, and it's probably in the mutex implementation. I did something I shouldn't have. And it won't be obvious. Oh, silly me, I don't remove it here. I think that's the interface. List. Remove. Yeah, it's just a node. Because when this is the only element, the only node in the list, the prev and next pointers directly point to the head of the list, so I don't need to actually give the list head. Which means that these two lines are enough to do the operation. Which is why most double linked lists are implemented by not using null pointers at the ends, but instead using addresses of the list head directly. There are fewer branches because of that, which is great. Okay, so I remove the waiter node, then I wake it up. That's much better. Okay. Let's disable the mutexes once more. Just to make sure that we haven't changed some weird side effect. Yeah. We don't change anything else, so it makes sense. Okay, so we have mutexes. I could implement condition variables now, but I'm afraid that I would finish at like midnight 30, and I don't want to finish late. So a last look at the code, and then as I usually do, there's a like 10 minutes, 15 minutes chat if you guys want to talk, because otherwise, you know, I could just sleep. I'm quite exhausted. A lot of work this week with pressure. Delicious. Yeah, not the object file. So here we add the mutex source, here we add the new error code, then we change the test in the main file, and in thread we have just reversed that. So what I'm doing here is not great. I'm going to make a single commit that includes those changes, and you should not do that. So yeah, do what I say, not what I do. The reason is because you want atomic commits, and what I'm going to do is not atomic. It's going to include a new error code, it's going to include changes in the thread module that have nothing to do with mutexes. Not a good thing. The reason I'm doing it is because I'm not going to keep the history. So the history will not be like, it's okay if it's just messy development stuff. It's going to be squashed into a few commits, like a single one for the initial commit, and then maybe a couple of commits for maintenance when I see, you know, typos, or if we ever implement something new, and then it will be clean. But right now I don't really care about that. So let's go over the mutex code one last time, but I think it's yeah, that part was already quite good, except that missed removal. Okay. Okay, that's fine. The header just has the interface right now. Yeah, okay. Quick question, what's an ARM64 assembly instruction to drop into the debugger? I don't know. Honestly, I really don't know ARM64, by the way. I know ARM32, and I'm really not sure that ARM32 applies well to ARM64, like on x86, for example. On x86, you have really good compatibility between the 32 and 64-bit modes. But the fact that Linux, for example, has two different architectures for ARM64 and ARM32 makes me believe that they are sufficiently different for me to not even try to tell you anything. And actually, I haven't debugged on ARM with such an instruction yet. Looks really different. Yeah, I don't really know, but I suspect. And I'm still going to try and merge it into my ARM32 port because I don't want to have two ARM ports. And when I said that I didn't really like ARM, it was exactly for that kind of stuff. It makes no sense to have so many differences between 32 and 64 bits. On Intel, and actually it's not Intel who did it, it's AMD. AMD wrote the 64-bit specification for x86, and it's great. Great in the sense that they made obsolete and actually removed truly obsolete stuff like segments. And everything else, almost everything else, is the same thing in 64 bits, so it's very easy to write code that works on both. On X15, the same code works on 32 bits, 32 bits PAE, and 64 bits. And when I say the same code, what I really mean is the same architecture. It's the same, like 90% is the same code. It's exactly the same files, almost the same compilation options, and you have a few if-defs, a couple of if-defs here and there to take care of the few differences. There are manuals, two separate sections for ARM64 and ARM32 instruction sets. No, that makes sense. The instruction sets are, well, I can imagine that it makes sense. For me, like as a developer, as a user of those manuals, I wouldn't be too surprised if there were two instruction sets. That's okay. But what I really mind is that they have two separate ways of handling the system, like two different system programming guides. That would be really annoying. And what I'd really like to see something like Intel did, well, AMD in this case, which is here is how we did it in 32 bits, and here is how we do it in 64 bits compared to the 32 bits, you know, just the differences. Or not, they could state the entire thing, but you would realize that it's almost the same as 32 bits. I don't really care about the presentation itself, but mostly the fact that it's very close, and so that you can make assumptions that are the same, which makes your work just easier and faster to do. Okay, so the code is on GitHub, right there. I should really add it to the stream page. Not finished yet, but really like quite usable already. So what I'm missing is condition variables and timers, and I let Metal Snake handle the timers. Should be quite interesting. They're not like, I wouldn't say they're optional, but at the same time for what I want to do, which is have a shell in the kernel, they are. I don't need them for the shell, I need condition variables instead. And actually I don't really need condition variables because I could already use preemption, thread sleep, and thread wake up. But I want a use case for condition variables to show people how condition variables are one way to implement them. Probably the most simple way to implement them. to show people that condition variables are just an abstraction to make threads sleep, and why it's important to strongly couple the shared memory that you are sleeping on, basically that you're waiting for to be modified, and the wake-up call that is going to signal that the memory has been modified, so that you may awake and use the modified shared memory safely. So that's already what we do with thread sleep and thread wake up. But condition variables are the most standard abstraction to do that in a safe way. So this will be my use case. No semaphores, although they could easily be implemented with condition variables and mutexes. But I don't want semaphore. Like I usually discourage people from using them. Okay. Actually, let's make the kernel run if you guys want to talk. Oh, it's not printing anything. Shame. Oh, also, it's not volatile here, but yeah, this thing acts as a barrier, which means I don't need to make that variable volatile. Okay. So if test counter modulo, say 1 million, so once in a while we're going to print the name of the threads, although it will only be one of them, the one which happens to have that condition true. And it looks quite low. Slow, sorry. Yeah, so it is using 100% of the processor, and it is quite slow, so maybe I was a bit greedy here. Oh, I added a 0. Looks better. Although the way I implemented it means that it's always test1 which is going to print that. So let's see, how could I change this so that it's also test2? Because I want both threads to report progress. Something like this. Okay. So yeah, I can see that you guys are already sleeping like me. I'm gonna stop the stream. Thanks for watching, have a nice weekend, enjoy life. That's one thing I really like to say, but I mean it. And right before I go, here is some music. This one is, which one? Yeah, this one is nice. The old harp. No. I really like this one. Okay, let's go for this one. Good night.